Hey everyone, my name's Xin Zhang, and today I'm reviewing the paper of fault attacks on STRNGs, impact of glitch temperature and underpowering on randomness. It's a pretty fun topic and pretty fun paper to read, so I'm really excited to share this paper. This is table of content. We'll talk about introduction methods, experiment setup, results. There's no lessons learned, and finally the conclusion. Okay, so introduction. So first, there are two concepts you need to know first. FPGA stand for Field Programmable Gate Arrays is very commonly used in a lot of systems, especially in a security system. And inside the FPGA, there's a component called True Random Number Generators, or TRNGs. So it produces keys, nonce, and of course the random numbers. So traditional TRNG will be sample from the ring oscillator, uh, and this component is less reliable. So uh, and being easy to attack. So a lot of the hardware attack will target this RO, like they use power glitch, clock glitch, temperature variation, and the powering. So someone come up and introduce a new improved way for the random number generator. It calls self-time ring uh, TRNG. Okay, and the right side is the structure of STRNGs. So basically, there's a self-timed ring, and it will goes through five delay flip-flops and finally generate a random beat. All right, so in this study, they want to evaluate the false attacks on the STRNG uh, using the uh, previous attack method I mentioned, which are very effectively on the traditional TRNG. And they also want to demonstrate the controlled manipulation of TRNG output to prove they can precisely control, uh, basically precisely hack the device to get what they want. And they also propose a simple countermeasure to mitigate uh, these issues. Uh, so methods. So first, these are the attack overviews. So they want so all the attacks are targeting the STRNG, and they are focused on the timing violation. So in the entropy extractor, basically they want to trigger the FPGA's timing violation. So below is the method they used. The first one, clock glitch attack. So in a nutshell, is they are overclocking the device to short each clock period. There are some key parameters inside this technique. So first, the injection timing of the attack should be very precise, and they also need to control the attack period, like the duration. Like if you only make one single glitch attack, then that that's not effective. It should be like control exact numbers of the glitch happens. And the objective of this method is to like force the circuit to sample the same guitar realism twice. Okay. Then the power glitch attack. So basically is injecting some sudden voltage drops, and it will cause the temporarily increase of the delay in the combinational logic, and and to compare the results, they also use underpowering, which will cause the permanently increase the delay. And because the attacker also need to precisely control when the drop happens, so uh the underpowering. Oh, they mentioned sorry guys, I missed the underpowering attack. So they also introduced the underpowering attack. So basically just drop the uh power power supply to lower than the normal working voltage, and they want to see if that will impact the result. Okay, that's the underpowering. Okay, then they also tried the temperature variation attacks. So basically, they are increasing the room temperature and see if that will impact the STRNG. Okay. And finally, they have the fault analysis and countermeasure. So they will they will observe the monitor the TRNG output and see if they are biased or uh, reduce the randomness. And they will analyze their result behavior before the injection or after the injection. Yeah, so let me check the node. Yeah. So they will determine how injected faults bias the output by comparing the pre-fault as a baseline and post-fault behavior after glitch injected. This is their experiment setup. So for the device, they use the Spartan 6, and yeah, they have this kind of setups. And for the system configuration, they use 1.2 volts as a normal voltage and clock at 60 megahertz. Yep. For temperature, they use the PTC heater and PT100 sensor, and they will raise the temperature from 35 Celsius to 85 Celsius. And please be aware, this is room temperature. It's not overheating the board uh, to to give like extra voltage to overheat it. It's just adjusting the room temperature. And they also have another Spartan 6 board to control the clock and power glitch using the USB. They also have another FPGA extension board to ensure everything is synchronized. And for the voltage variation, they'll change it from 0.7 volt to 1.26 volts. And this is the result. First, the high temperature fault attacks. So they tried to raise the room temperature to 85 Celsius. And the result is there's no significant bias, basically no much impact on STRNG. Now it's a underpowering attack, so let's reduce the power to 0.7 volt. So I didn't show the 1.2 volts on the right because they are testing the underpowering. So yeah, so during underpowering, the cycle just being like there are some small bias happen, but there's no much significant impact on the result. The bias was removed after after post-processing. And then we come to the power glitch attack. So at a nominal voltage, at 1.2 volts, there's no effect on the measure. Okay, then uh, oh yeah, so at when they set the frequency to 40 megavolts with longer glitch, there are some uh, bias happened, and as as the image show here, like when you apply a small glitch, then the output will be impact a little bit. This is random bits, and when they extend the glitch, then the impact will become very significant. So right here, there's all uh one output, one bit, like 0, 1, output. Yeah, but they also mentioned so there's no much impact on the self-time ring, but there is a significant impact on the TRNG, the component itself. Basically, I mean, there's no impact on this component, but at the output, there's a significant impact. Basically, this part is being impacted. Okay, then comes to the clock glitch attacks. Uh, this is where I feel it's fun. So, basically, they injected more like clock to cause the device overclocked it, and it's over. The normal working speed is 60 megahertz, but they overspeed it to 90 megahertz. And because they can uh, control the clocking speed, so they want to prove they can manipulate the output. Then they control the TRNG to generate a I-shaped signal. Uh, like let's draw an eye on the 2D graph. It's pretty fun to see. All right. They also talk about some countermeasure and some discussion. So they mentioned first uh, the FPGA can like introduce a ripple XOR tree to reduce the critical delays like here. And they also mentioned they can also introduce glitch-free clock generator to filter out some short glitch. And okay. Finally, this is their conclusion. So at the fault attacks, they proved the power and clock glitch can adjust the STRNG outputs. There are some risk at this part that need to be noticed. And but it also proved the robustness of the STRNG, which is the temperature and underpowering has no impact on the component. And as a countermeasure, so they mentioned Ripple XOR tree and glitch-free clock generator can reduce the glitch from happening. Finally, they give the future work, so they want to explore more advanced post-processing, higher frequency attacks, and also some passive attack defenses. And that's it. Thank you for listening. I know I might speak a little bit slow, but hope you get the full scale of the image of this paper.